is Lukas Fittl, who's going to be telling us all about how to optimize Postgres queries. Take it away.
Does the microphone work? Yes, wonderful. Perfect. All right, so you might be wondering, why are we talking about Postgres at the Python conference? But the truth is, I think many of you are using Postgres, including the last talk where we saw pgvector mentioned, which is a Postgres extension for vector databases. And so today I want to essentially teach you how I debug queries, because what I find most useful is essentially to learn other people's mental model, and this is what I've essentially learned over many years of working with Postgres. We're going to talk about 5 things, and this should, get us nicely into lunch, I think. So we're going to talk about what's my iterative process for optimizing queries. We're going to talk about how to use explain in Postgres effectively. We're going to talk about cost estimation and selectivity and how Postgres uses that, and how you can reason about that. And we're going to talk about join order and parameterized index scans. And I'll leave you 5 actionable tips. My goal is that even if you don't work with Postgres day to day, it's just the database you're using, this will help you work better with the people on your team that do have to care for a database, that probably have SRE in their title, or data engineer, data platform engineer. And so the goal is for you all to essentially have more context on what their day-to-day work looks like. So typically, the iterative process of optimizing a query starts with code. In this case, I just picked the next best, Django code here. And usually, in this case, you can see there's just very simple, we're looking up some things, we're filtering by an ID, right? That's the simplest perspective you would probably have on interacting with Postgres. Now, oftentimes when we optimize performance, we start looking at traces. And so one of the important things to understand is that there are certain kinds of problems called N+1 queries, which will show up in a trace as essentially a lot of single queries, in a big request. But they're all very fast, right? They're like 0.01 millisecond type queries. And so we're not going to talk about that today. If you're trying to identify N+1 queries, you should use your application monitoring tools, or just look at the requests you're running. We're going to talk about when things are slow. So here is a screenshot of a honeycomb trace that we use ourselves. And here we can see, let's see, it's like 30 seconds of runtime. In total, it's like 25 seconds or so are spent with the query, right? So this is the kind of thing where we really need to understand what is Postgres doing. Like, why is Postgres spending 25 seconds running a query for us? So when I debug a query, I have to start with a SQL statement, right? So first step is, if you usually work with code, get to the actual SQL statement. That can be done from database side, like you can log the slow queries, or you can just use your tracing system if you have one to get the actual query text. And then really the most important tool we have is explain analyze, and most importantly the buffers option, which I'll talk about in a second. And the idea is you literally just put that in front of your query, and then it lets you optimize, lets you understand what the database is doing, right? So this is your entry point into the Postgres debugging world, and all the rest we're going to talk about today is how we can actually make use of that output, because it's essentially a bunch of text, right? Like Postgres is, in a sense, very good at that. Like everything is accessible. Like you don't need to use any tools by any vendors, or have any fancy graphical tools. You just need to have a way to run a query. You put explain in front of it, and then you get a bunch of text out. And so my goal is that I can help you understand a little bit better what the text looks like. Now, in the Postgres community, we have, we're a community as well that works in this database. And Tom Lane, who is one of the principal authors on the Postgres Planner, has been for many years, said one important thing in a talk about 13 years ago, which is that the planner's task is fuzzy, right? So like when Postgres plans a query, there isn't the perfect plan for it to run. And so when we're debugging what Postgres is doing, we need to understand that Postgres has its own heuristics to come up with these plans. And so really the Postgres' planner's responsibilities are, it needs to find a good query plan, right? The query plan is like, how does the query actually get executed? It doesn't need to spend too much time or memory finding it, hence not the perfect plan. And it needs to support the extensible aspects of Postgres, right? So pgvector was mentioned earlier, that was able to be supported without Postgres itself needing to change. That was just an extension that was added to Postgres, and that's really both amazing, but it also means that it's a bit challenging in terms of how Postgres plans these queries for us. Now, for us, when we work with Postgres, it's also important to understand what Postgres will not do for us. And first of all, it will not find all the possible plans. It will also, not change a plan when its expectations don't hold true. So let's suppose Postgres realizes there's a lot more data. Postgres will actually not change what it's doing. And it will not keep track of execution performance. So this is really the most important thing. We as humans have a job here, which is we need to understand that if things behave badly, Postgres will happily keep doing the bad thing. We actually need to intervene and take action. And I'll get there in a second of how we can actually take action. So My basic debugging loop is you have a slow query, and then I'm going to benchmark the query. I'm just going to run explain analyze in front of it. Then I need to form a thesis on what to change, right? And this is where the mental model comes in, where you kind of need to have a mental model of how the database works. And then you need to try out the change, which might be a configuration change, might be adding an index, for example, and then you actually run explain analyze again. Then ultimately you want to make that permanent, right? So then at the end you say, well, it works. Let's figure out how to do a migration, do all the fun testing things I mentioned in the first talk today. Like all of that stuff doesn't have to happen as you're iterating. That really should happen once you've validated what the right approach is to optimize the query. Now let's talk a little bit about what this explain command does. So there's 3 things to understand here. First of all, if you just put explain in front of a query, this gives you the plan that Postgres is gonna execute, but it doesn't actually execute it. So it just gives you the heuristics, but it doesn't give you the actual performance. Explain analyze adds the runtime statistics, so it actually runs the query and tells you which part of it was how fast, how slow, where did Postgres spend time. And then explain analyze buffers, that's essentially an extra option we can add to get more information on the I/O. Let me illustrate this a little bit, and hopefully, well, probably hard to see in the back, so I'll walk through it. So again, we have text output, right, and here we have essentially 2 plan nodes. These are essentially parts of the query that get executed. And this is very simple here, so we just have a single table called test. And kind of at the bottom of the output, we can see it says parallel sequential scan on test. So it's essentially doing a sequential scan on that table. And because it's parallel, Postgres launches 2 processes, and then the gather node kind of groups that back in into one result. And so here we can see this is just the estimation of what Postgres is going to do. Now, one thing to note here is that these numbers you see in these plans and these kind of explain outputs, they are including children. So it's a tree, and if you have the gather node here at the top, it says 97,366, and underneath it says 96,366.18. So there's like a teeny tiny difference here, and so the top node is really cheap, but the sequential scan is really expensive. And so you've got to make sure to run the math, because Postgres tells you always the including the children cost on these plans. Now, if we add analyze, we see that it actually tells us what was the plan doing. It took 307 milliseconds in this case, and it tells us that a bunch of rows were removed by this filter, right? So we're sequentially scanning our table, filtering out things, and so this is very important information because this is a really bad plan, right? Like it's really slow to just remove all that row manually. Now, if we add the buffers option, it will tell us how much I/O was being done. And it gives us information here where it essentially says I/O timings, and it says here is 95 milliseconds spent on I/O time, and it tells us also how much pages essentially were loaded, so how much bytes ultimately were loaded. And this helps us assess how much work is this query doing on the I/O side. And most of the time when I've seen production query problems, they are I/O related, right? So this is why buffers is so important, is because it tells you how heavy the query is on the I/O performance side. Now, as mentioned, I'll skip that, so I just said it. The other thing to note, and this is definitely going to be easier to read when I toot out the slides later, but there are dead rows in Postgres and bloat in Postgres. So sometimes when you look at these I/O statistics, you can find out that a table is bloated, and so things are slow because of that. You also got to be a little bit careful because Postgres will have a fly on my nose apparently. Postgres will tell you both how much data it read and then how much data was already in the cache. That number about the data already in cache, that essentially doesn't, it can double count because sometimes Postgres accesses the exact same data again. And so you just got to be careful when there's lots of millions of pages being hit. That sometimes doesn't necessarily mean that you loaded that much data. It just means that Postgres re-accessed the same data all over again. Last thing I'll say here on the basics of explain analyze is it itself has overhead because Postgres tracks more statistics. And so if you're trying to optimize a query, it does help to actually run the query by itself also. So as you're trying different things, just run the query without any explain analyze because, for example, here, there's a bit of an extreme case on the right side. We have select count star, which takes 340 milliseconds if we just run it by itself. And if you run it with all the options of explain, analyze, buffers, and timing on, it's about twice as slow. This is the extreme case, but generally, do rerun things just without the explain analyze. All right, so this is the basic. Hopefully that made sense. Now, I want to talk about 2 important concepts that you need to understand when you actually look at the plans and you try to understand what happens. So first of all, cost estimation selectivity. So Tom Lane, again, said garbage in, garbage out applies here. So cost estimation drives what the planner is doing. The planner tries to decide which plan to choose, right, which indexes to use, how to join things together. And so if you have bad data, if you have bad statistics, then Postgres will produce bad query plans. And so just so you know, all these things in that text have meaning, essentially. There's a startup cost. There's a total cost. That's really the most important thing to look at. So it's the second number in the cost because it tells you what the planner tries to minimize, right? So that ultimately it's an algorithm that tries to say, how can we get the plan with the lowest cost? And then it also estimates how many rows it thinks it's going to output, and it's going to estimate how wide these rows are, right? Again, an example of PGVector would be PGVector, like vector embeddings, can be extremely wide, like a lot of data, versus if you just have a bunch of small integers, that's very different. Now, what is cost, right? Like cost seems like a kind of, what does that mean? Well, it is actually kind of arbitrary. So it's more like a currency, right? Like it's, again, essentially, it's just trying to say, how do I compare two paths? We give both of the paths a cost, and one of them is going to be cheaper, and so we're going to take the one that's cheaper. So you can answer the question, what is the cost of a sequential scan, right? Like just reading the full table by looking at the Postgres source. This is C code, and it's a very simplified C code at that. But in a sense, really the simplest thing it does here, it just says, how much cost does the sequential scan have? That's 1 usually. And then it multiplies by the number of pages in the table, like how big the table is, and that's the cost of a sequential scan. Very simple, right? Obviously, a lot more complex examples exist, but you can read the source code. Like Postgres has actually pretty good documentation in the source code also. So if you're ever interested, why is the database doing these things, and you're okay with reading C code, then definitely just look at the actual source. Now, index scans similarly, they have their own estimation. Now, index scans do have are kind of flexible in that because there are different kinds of indexes, right? So PGVector, again, for example, introduced 2 different index types, IVF flat and HSW. And so both of these have their own cost estimation functions. The B-tree index in Postgres has a different way of estimating costs. And so that's really dependent on index type. But then ultimately what we'll try to do is we'll try to say, how common are the values that we're looking for? How selective are they? And so that's really the thing here is, and this is the last time I think I'm quoting Tom Lane here, is selectivity is the hard part, right? Selectivity is where really a lot of the good or bad of Postgres' query planning decisions come from. And there's a function that tries to come up with these things. The most important thing to know is that Postgres will multiply out selectivity. So if you have where x equals 1 and y equals 2, it will multiply the selectivity of those two. So numbers get really small if you have a lot of ands, essentially, in a query. And a small selectivity number means it's very specific, like very few rows being returned. Now, we can see this in the explain plan by looking at the row count, right? So this rows estimate, that's really driven by the selectivity estimation that the Postgres planner is doing. And as mentioned, really the worst cases are when Postgres thinks clauses are independent, but they're not actually independent, what's called functional dependency. And so an example here, a little bit longer, would be A equals 1, B equals 1, C equals 1, D equals 1, and E equals 1. But what if all the A equals 1s also automatically mean that B is 1? Or if there are no C1s that also have D1, right? So if there is these relationships between the values. Postgres doesn't know that by default. And so here's the first thing you should try if you've never tried this on your Postgres database. There is a thing called create statistics, which is an explicit command you need to run. Postgres will not do this for you. But what you can say is you can say create statistics. I use the example of barn cats here. So you can say a barn cat has a cat name and a barn ID. I guess this is barn number 1 here. And we can tell Postgres to essentially collect dependency statistics. That's what dependencies type there. And so the idea is that, after we run analyze, which, essentially calculates these statistics, Postgres will then know if a given cat name exists, how likely is it that the barn ID is always going to be the same. Now, probably not very likely, right? I imagine. I don't know how people name their cats around here, but I'm sure you find very common names across different barns. And so this is actually not a good example. A better example would be if you look at US zip codes. Most zip codes, I looked this up earlier, it's like only 41 zip codes go across state lines. All the other zip codes are essentially like always in one state. And so that means you have a very high functional dependency or correlation between a zip code and a state. And so if you had a table of US zip codes, you could say create the dependency statistics on zip code and state. And in Postgres, if you had a query where it was like where state equals California, zip code equals 94116, then Postgres would know that that essentially means the same thing. Like if you have just the zip code or the zip code and the state doesn't filter it down further, essentially. So this is very important if you have that kind of data. If you just store information on a bunch of barn cats, not as much a problem. But if you have a lot of zip codes, then you should essentially make sure that you create this on your production system so that Postgres can give better query plans. Now, there's a similar problem for joins. So when Postgres joins data together, the data also, there's estimations around how many resulting rows are there going to be, right? Because you're matching up two different tables. Very complicated stuff. You know, read the Postgres source. I put the links there in the slides if any of you are really interested. But the point is Postgres uses what's called most common value lists to understand how likely it is that the two tables are matching, essentially. And so the thing you can do is you can increase what's called the statistics target so that Postgres collects more samples, right? Like remembers more names, essentially. So I think one of the barn cats was called Pete, for example, right? Postgres will remember if there's enough barn cats called Pete, it will sample the table, and it will essentially say, well, by default, store 100, but let's suppose I have lots of barns, lots of cats, then I might need to raise the statistics target so that, if different barns have a lot of different cat names, we can actually match that up with whatever table we're joining with. And to be clear, to make this work, you would need to also do this, set statistics on the other table you're joining, right? So the idea is both tables have good statistics, you join them up, and Postgres has enough information to make an educated decision. Now, join order and parameterized index scans. That's really the last bulk of information here, and then I'll close with a few tips. So this is one of the things that wasn't as clear to me actually when I started working with Postgres. I want to say like 14 years ago now, but it became a lot clearer as I looked at more plans. And really parameterized index scans is the thing I want you to take away here. But let's start with what does join order mean? Like how does the planner even work with different tables? So when the Postgres planner looks at a table, or looks at a query, it tries to say for each of the tables involved in the query, it's going to come up with two different ways of using that particular table in the particular where conditions. First of all, it's going to try to find the cheapest path, meaning if there's a really good index scan, it's going to try to use that. If there's no index scans, it's going to make a sequential scan, for example. Now, second, it's also going to make a decision. It's also going to remember a case where the scan on that table is parameterized. I'll get back to that in a second. Now, in a simple case, this is a non-parameterized example. We're joining three tables, A, B, and C, and we have b.x equals 1, c.y equals 2, and A, we have no filter, right? These are called base relations, they're just tables in a sense. And so you can see here that A, we are not filtering anything, right? We're just saying A, like we don't know which A's, so we're just going to look for all the A's. So we have to do a sequential scan. On B, we can do an index scan if there's an index on X in this case, which there is. And on C, we can also do an index scan, again, if there is a index on a Y column, right? So Postgres could first essentially, like scan all these indexes and then combine the information. Now, actually, sorry, I lied earlier. There's a fourth Tom Lane quote in here. He does pretty in-depth talks, so I apologize for quoting him 4 times. But finding the best ordering of pairwise joins is the hard part, right? So we have all these tables. How do we combine them? And so in this example of 3 tables, we'll start with 2 of them, right? So we have a sequential scan on one, index scan on the other. The simplest example of a join in Postgres is a nested loop join. That means we're taking one row out of A, we're kind of matching it up with one row out of B. We just keep going essentially. And we're doing, to be clear, in this case, the nested loop join actually does a lot of small scans on the second table here. Now, this gets more complicated, of course, as we add more tables. So here we add, the table C essentially into the mix, and so we first join A and B, and then we add C, and so it's A, B, and C, right? Now, the important thing to understand is there's a choice here that Postgres makes for us, and that might not be the right choice, or we at least need to understand what the choice is. So for example, Postgres may also choose to first do A and C, and then, combine them together to AC, essentially, and then add B into that, and then ACB comes out. In this case, again, 2 nested loop joins. This might perform worse or better, and Postgres will try to come up with an estimation of what makes sense. Now, we can represent join order, and this is, again, probably hard to read, by using parentheses. So we can essentially say, parentheses open A and B, and then, that's essentially inside the parentheses, and then we say C, meaning we first join A and B, and then we add C into the mix, and that's the result, right? There's also an order to this, so ABC is different from BAC. because in this case it means we're first getting A, and then we're searching for all the B's, and then we're searching for all the C's, versus if we did BAC, we would first get B. And this gets pretty expensive, actually, for Postgres to calculate, right? Like this, there's an n factorial of different join orders, depending on how many tables you're joining. And so after you have 12 or more tables, Postgres has a whole different way of doing this. Less than 12, it essentially tries to find the perfect join order. More than 12, it just uses genetic query optimization, which sounds fancy, but doesn't really work that well in most cases for me, in my experience. And so I would say, that's essentially 3 essential choices in terms of, what causes a good or bad plan, which is the scan methods, right? Index scans versus sequential scans, the join order, and the join method, which is nested loop join, hash join, merge join. These are all essentially related to each other, because if you don't have an index, then, things will look different. And also, a join order can change for the same query. So this is some analysis that I've done as part of the hackathon project, but we essentially saw for one particular query, we saw 2 very different join orders, and that was just because the selectivity of kind of individual query values, like parameter values, was different. Now, parameterized index scan, what does that mean? So here, again, we have a big wall of text here, right? We have a hash join, and in this hash join case, we have a sequential scan on the table T2, and then we have a bitmap heap scan or bitmap index scan on table T1. So the idea is they're both independently essentially looked up, and then like one of them gets hashed, and then they get joined together. Now, an alternate plan for the exact same query, right? So the query doesn't change here. It's just a plan changing. Would be a nested loop join, and then on the second table here, on what's called the inner side of the nested loop join, we see what's called a parameterized index scan. And this, in a sense, is very simple, but you really got to train your eyes to see these in this text output. So parameterized index scan means we're using a result from one of the tables to scan the other table, right? So here, we're matching up, like in the join condition, we have t1.id equals t2.t1id, very typical in many applications. And so Postgres, in order to be able to scan one of the tables with an index on these join columns, will need to use what's called a parameterized index scan. And so here, first, it essentially gets all the data from T1, and then for each of the T1s, it does an index scan, and it matches up those conditions. That only works for nested loops. So that's the most important thing to understand. If you need this kind of index condition, if you need to have index lookups based from data from one table to find data in the other table, then you will need to have nested loops, and nested loops are oftentimes inefficient. So it is not necessarily a good pattern to have only one join condition that essentially lets you filter a table. And again, it looks like plans will look very different if that happens. Parameterized index scans have to be in the inner side of the nested loop, so join order matters again. Now let me close with 5 actionable tips, and then we should be ready for lunch. So first of all, if your explain shows a sequential scan and you're scanning a large table, then add an index, right? If you just, on a tiny table, like a few megabytes, you don't need an index. Postgres might even choose not to use an index. But if you have a large sequential scan that's slow, really it's an indexing problem. So none of the things we talked about really matter that much. Just look at, how to create the right index types for your queries. Second tip, use explain analyze buffers to understand how much data is loaded from different tables. But be aware of the hits counter sometimes being off. Right? So that's one of the things that really does need interpretation. But this, I think, is not the default, right? So you really got to remember to add the buffers option, but it will tell you which parts of the query are most I/O intensive. If row estimates are off and you have a bad plan, there is a create statistics command, or you can increase the statistics target. If you do that, don't forget to run the analyze command, which will make sure that you essentially have actually collected data. Fourth, if you can, and especially a typical case where this would be a multi-tenant app, add additional join conditions. So here we have, where customer ID equals 1 to 3. Very typical example that I've seen is you have like one table, you do the where customer ID 1 to 3, you join the other table, which also has customer ID, but you're only specifying customer ID once. That's actually not good in many cases, because Postgres has to use a parameterized index scan to look up the other table. So if all your tables have a customer ID, it can be helpful to just explicitly add these extra where conditions, because then you're essentially enabling other join types to be used, oftentimes leading to better query plans. And then last, query optimization is a team effort. Part of the reason why I thought this was important to talk about here is because I often talk at Postgres conferences with people on stage, off stage, and I don't think the Postgres community goes out often enough, although we do try to make an effort, to talk with other communities like the Python community. And so my hope really is that you all find it interesting, or at least some of you find it interesting, to think about how do queries get optimized, what is the debugging loop here, right? Like how can we essentially do performance optimization for our database? Because I kind of hate the situation where it's just delegated to the SRE or data team. Like I work with many of those teams and they're just often overwhelmed, right? Like they just have like 2 people for 400 engineers and they get all the Postgres slow query questions. And so really I think we need to empower everybody who works on an application that uses Postgres to optimize queries because they have enough context, right? Like you know best what your application does, which where conditions you could add or which indexes. Makes sense. And with that, if you want to hear more about these kind of things, I do a weekly video series on YouTube called 5 Minutes of Postgres. Feel free to find that if you search for PG Analyze, which is our company's YouTube handle. And then I'm going to tweet out the slides on Mastodon as well. And I'll use the Nbpy hashtag. But you can find me on Mastodon or send me an email if you're interested in these things. Happy to chat more about this. Thank you.